Welcome to Renewable Energies. It's a little bit sad here, everything empty. I just can't speak to the camera. But I guess for most of you, it's similar, sitting at home in front of a screen. But actually, it were just a few of you who attended, whom I had the pleasure to talk to. So today, it's the empty room, but nevertheless, we'll try to make the best out of it. Okay, so let us a little bit review of what we did last time. What we did last time, I said. Last time we had actually, I hope you agree, we had kind of a fun lecture where we tried to calculate the Earth's temperature. And what we used was equilibrium of radiation. So radiation that comes from the sun has the equal amount of radiation that the Earth radiates as a consequence of its temperature. And then we went on a little bit and actually also established that there should be an equilibrium of radiation for the atmosphere. And in this way, we created a simple model for the greenhouse effect. And I hope you enjoyed that lecture. Today, I will pick up from where we left 2 weeks ago, actually. And what we did there is also kind of an interesting story, namely an extension of the Canoe machine, of the ideal heat engine, such that we can take into account, again in a simple model, that we can take into account irreversibilities. Yeah, so the Canoe machine, by definition, is a reversible machine, so produces no entropy. And now we want to introduce a heat engine that has reversibilities. And in order to start, what I did was that we looked or reviewed quickly the Canoe engine, so that you see here. Yeah, it's defined as a machine that creates, of course, mechanical work, which is the entire goal actually most of the time of such a machine. And in this machine, what comes in is heat, Q1, and what goes out is, again, heat, but at a lower temperature. And what also goes in is entropy, and because entropy is conserved for a Canoe engine, we know that both are equal, whereas, of course, the heat that goes in and that goes out is different, and the difference is the work that the machine puts out. So a very idealized machine. And in the homework problems, actually, Martin Bayer explained to you, or you did the exercise of using specific processes, isothermal and adiabatic processes, in order to see how such a circular process can go on. Another example would be the Stirling motor that can also be modeled as an ideal heat engine. And what we found out was the efficiency, the maximum possible efficiency, defined as the work that we can get out divided by, the money that we kind of have to put in, right? So Q1, this can be gas, hot gas, so burning gas, or it can be burning coal or nuclear heat or whatever, right? So this is what you have to put in, and this is what you get out, and the ratio of both is naturally the efficiency. And the maximum you can get, so for this ideal heat engine would be this here. So now the next thing is that we discussed endoreversible heat engines, and what endo means, it's Greek, and there was a correct criticism last time, namely that it should not read eta here, but nu. Right, so should read like this. So somebody made this remark. It's Greek for internal, and what it means is that we indeed have an ideal Canoe engine in the inside of this engine, and we have this intermediate temperature level which is coupled to the surrounding. So you see this open rectangle here as opposed to this closed rectangle. So this is coupled to a heat bath where we kind of assume that there's an infinite source of heat available there, right? So if you have a big enough gas tank or nuclear fuel, then this certainly makes sense to say it this way. And to give a specific example, let me show one slide here. One slide. So where do I have my remote? Here I have the remote. So what you see here is a nuclear power plant, right? And as I mentioned, what we have here is this is the nuclear fuel. Right? And then you see that we have here a heat exchanger. So we don't feed in the nuclear heat directly into the turbine. So the turbine, if this is a very good turbine, then this could be this internal machine. So this so if it is very good, then this can be a Canoe engine that produces no entropy or hardly any entropy. So this would be the upper temperature bath here. This here would be the intermediate bath here. Well, and the lower one, so the T2, so right at the bottom, this would be the river. So again, the surrounding, and there's of course another heat exchanger. This would be the lower intermediate level. So you see that this endoreversible heat engine is not as artificial as it might look on first glance. So, and what we try now to do is to analyze this heat engine a little bit, and what we want to derive in particular is the characteristics of this machine. So in German, characteristics would mean Kennlinie. Specifically, what we want to know is how the work that the machine puts out, how this depends on the efficiency. A kind of a strange way to analyze a machine, but on the other hand, you will see that it makes a lot of sense. But we'll see this, not in a minute, in many minutes. Will take us a while. So the idea is that this upper heat bath here, that has been, in this example, the nuclear fuel, that this is coupled via a thermal resistor to the heat exchanger, to the hot heat exchanger. And we used Fourier's law for that. It looks just like Ohm's law. So you would take this as the potential difference here. This would be the conductivity, so the inverse of the resistance, and this would be the current, just to illustrate an analogy. And the same thing, of course, down here. And you immediately see from the definition of the entropy. So entropy was defined. Entropy is defined as the heat divided by the temperature. And you immediately see that, of course, we must have a temperature difference here, which means that such a thermal resistor, a thermal conductor, creates entropy. So this is clear. This is where the entropy comes from. No entropy generated here, but entropy generated here and here. Good. Again, we then started to define the efficiency quite in the same way as before, namely as the work divided by the heat energy. Heat energy is, of course, not a technical term, but I should just say the heat. So work divided by heat, and if you, if we use what we derived for the ideal Canoe engine, which is actually working in between these two levels, we get this expression here. Yeah, and then we try to establish a few things. Yeah? So it is of course clear that the first law holds in the same way. Yeah? So Q1 and Q2 here, the difference of both, this should be the work. And we also have conservation of entropy in between these two levels. Okay, yeah, so the next thing would be that we substitute these two equations up here, equation 2 and 3, we substitute into this equation 6, and we arrive at this point here. Yeah, and I mentioned that already last time, that we consider now this equation and this equation, we consider this a system of equations, and we try to eliminate those quantities that to which we don't have access. Yeah? So these are typically the intermediate temperatures, so these here. All right. Okay, so let us write that up quickly. So 4 and 7 can be considered as a system of equations. Yeah? What we do is we regard T3 and T4 as unknowns, and eta as the independent variable, as the given variable, and eta as given variable. Yeah? Again, sounds strange, but the idea is, of course, to calculate T3 and T4 as a function of the efficiency. So you ask the engineer to design the efficiency or to run the power plant at a given efficiency, and then what you try to calculate is which temperatures for these heat exchanges would result. Yeah? So this is reasonable. Because for a given engine, and a given environment, and a given environment, T1 and T2, yeah, so the temperature of, say, the nuclear fuel, and T2, the temperature of the river. For a given engine and a given environment, T1 and T2, as well as G1 and G2 are known. While the internal temperatures are not known, but we need the internal temperatures in order to calculate something for our ideal heat engine. Are not known, but needed to compute, for example, and in particular actually, the work W. Yeah? So, it's a system of equations. We can solve it. We can also ask Mathematica to solve it, and this is what I did. Yeah? So just the solution, I asked Mathematica to do it for me, but you can do it yourself, of course, but you can also ask any other symbolic mass program to do it for you. So we have G1 divided by the sum of G1 and G2 times T1, and now pretty much the same, just G2 in the numerator. And here we have T2 1 minus eta. That's equation 8. And a similar equation for T4. This is G1 divided by G1 plus G2, 1 minus eta T1, plus G2 divided by G1 plus G2 times T2. That's equation 9. Okay, what is next? So when we have the temperatures, T3 and T4, then we can calculate, then we can obviously calculate, so this one here, so then we can of course calculate the heat, the heat that flows. Yeah? So if we have T3 and T1, then we can calculate the heat. Yes, and then we can calculate Q1, and this is actually what we are doing. So when we know T3 and T4, we can calculate Q1 and Q2. And Q2. We are just interested in Q1 for the moment. Yeah, because what we said is that Q1, where is it? We said that Q1 is equal to G1 times the difference of T1 and T3, and T1 is given by nature, more or less. So what we know is equation, I think it was equation 2, Q1 is equal to G1 times T1 minus T3. And now if we plug in the above, then we get G1 times T1 minus G1 times G1, also G1 squared, G1 plus G2 times T1 minus G1 G2 divided by the sum G1 plus G2, and then T1 over 1 minus eta, and this can be simplified. So what we so we bring it on the same denominator. Then we have G1 plus G2 divided by G1 plus G2 minus G1 times G1 divided by G1 plus G2 times T1. I forgot a T1 here. And finally, yeah, the last term here, G1 times G2 divided by G1 plus G2 times T2 1 over T2 divided by 1 minus eta. Yeah? And what you now see is that we can cancel this here. Yeah? So this is the same term. And what I further do, and what I can now do actually is, so you see that we have here now G1 times G2 divided by G1 plus G2. This is the same factor as here. And therefore I decide to do an abbreviation. Yeah, so I just call this thing here G. Well, and this here of course also. Yeah? And if I do so, then I get that Q1 is equal to G times T1 minus G times T2, 1 minus eta. That's equation 10. Yeah, so this can be rewritten a little bit, yeah, so just a little bit more cosmetics. Yeah, so 10 can be rewritten. Now let me see what I did here. Yeah, I just factor out G. So what I get here is then Q1 is equal to G times T1 1 minus eta divided by 1 minus eta minus T2 1 minus eta. And this is equal to G times T1 minus T2 minus eta times T1 over 1 minus eta. That's equation 11. Yeah. So now we have an equation for Q1, and this we can actually immediately use in order to write down an equation also for the work. And this is what we do now. So we said that the efficiency is the ratio of this heat Q1, of the work to this heat Q1, right? And now we just can rearrange it and say that the work is equal to the efficiency times Q1, right? And this is what I'm going to do, and nothing more actually. Yeah? So what I say is, yeah, so from eta, which by definition is equal to work divided by Q1, we get that Q is equal to eta times, that W is equal to eta times Q1. And this means that the work is given by G times, well, and now just the eta in addition. So we have T1 minus T2 minus eta times T1 divided by 1 minus eta, right? And that's equation 15. Yeah. So now we could do different things. Yeah? So what I could do, of course, would be to just plot these curves as a function of eta. And eventually we'll do that. I can also plot Q1 as a function of eta, and also the entropy. All of these things we'll do, and these curves are called the Canelian, or in English, characteristics. But before we do that, we want to look at a few special cases, yeah? So to say limiting cases. And in order to kind of establish the logic, I start again at the Canoe Engine. Yeah. So we look for the thermodynamic modes of the Curzon-Alborn engine. Actually, Curzon-Alborn engine, I discovered a few days ago that the Curzon-Alborn machine is called Curzon-Alborn machine because it was introduced by two other gentlemen, namely Novikov, and he wrote a paper approximately 20 years before Curzon and Alborn on the efficiency of atomic power stations. This was the title of this paper. Probably it was in Russian. And even a little bit earlier, a year earlier, a Frenchman likes of the name Jean Padet, I'm not sure, wrote a paper on les centrales nucléaires in 1957. So the example that I brought with the nuclear power station is not so far-fetched, but actually what we derive is, of course, valid not only for nuclear power plants, but for any power plant, in particular also for solar power plants. Yeah? And we'll have some discussion. What is the fundamental difference between a nuclear power plant and a solar power plant on the one hand side, yeah, so you heard right, and a gas-fired power plant on the other hand. Okay, to this end, let's discuss the thermodynamic modes of the Curzon-Alborn machine, as I call it. I should call it Novikov, Champerdet machine. Anyway, yeah, so what you see here is how important it is to write a good paper. I mentioned that Curzon, that one of both Curzon or Alborn, I don't remember. Well, I can look it up. Yeah, actually, Curzon and Alborn, they wrote a paper in the American Journal of Physics. And this is the Journal of Physics Teachers, a very prestigious journal in the US. So they published that paper there, and everybody cited it. They wrote a good paper and got more credit than they deserved, actually. Anyway, back to the thermodynamic modes. The thermodynamic modes of the Curzon-Alborn machine. So, and as I said, we start with the Canoe machine. So for reference, perhaps I write, so for reference, first the Canoe Engine. So the thermodynamic modes of the Canoe Engine. Yes, I'm sure that some of you know that. So I'll discuss the modes of a machine in the narrower sense, but then also a refrigerator, a heat pump, and these things. Yeah? So for the Canoe Engine, we can distinguish the following cases. Namely, that eta is smaller than 0, that eta is larger than 0, together with a positive work, so that the machine actually does work, And finally, we can also use, or we can also have a positive efficiency, where the work and thus also the heat is smaller than zero, right? So maybe for illustration, I show the picture of the Canoe engine once again. No? So this one here. So we start with the perhaps a little bit strange looking case that eta is smaller than zero, right? Yeah. So eta smaller zero. What this means is, so if we substitute this into the Canoe efficiency, namely that the efficiency is equal to 1 minus T2 divided by T1. So then we get with eta is equal to 1 minus T1 divided by T2. So let me try to catch this fly here. Got it. So with this we get the T2, no, the T2 is larger than T1, right? T2, the lower temperature level, the nominally lower temperature level is smaller than T1, so this is here hot, is larger than T1. This here is hotter in this case. Yeah? In addition, we know that the work and Q1 have opposite signs. Yeah, so in addition, W and Q1 have opposite sign. So the case where actually, well, the case where Q1 is negative. Yeah? So if Q1 is negative, then the work can still be positive. Yeah? So if Q1 is negative and Q2 is and W is positive, then it's actually just a Canoe machine, a regular Canoe machine, just drawn in the wrong way, kind of. Yeah? So if this is hotter, and this is the heat that flows here, and here it flows to the colder part, then of course this machine can produce work. Yeah? So the case where Q1 is negative is trivial because it's the same than a regular heat engine. Yeah? So let's write that. Yeah? The case Q1 smaller 0 is trivial because it is equivalent to just flipping the index to Q1, to just flipping Q1 into Q2. Yeah? So this is the same situation as, well, the kind of defining case of a Canoe machine. Yeah? So therefore, the interesting case here would be without loss of generality, WLOG. Yeah? So we can assume that Q1 is larger than 0, right? And this means heat flows from the lower temperature level to the upper one. Heat flows from the lower level to the upper one. It is clear that the machine wouldn't do this, it doesn't like to do that. Yeah? It doesn't do this by itself. You have to persuade the machine, physics to do that. And what you do in order to get this is that you put in work, right? So, and of course you know that machine very well from your home because your refrigerator is just doing that. Yeah, so there you force the heat to go in the, well, kind of unnatural direction, namely from the lower level, from the inner of your refrigerator to, well, to the surrounding, to your kitchen where this refrigerator is located. And you know, you have to run a motor or something like that. Yeah, so you have to put in work. Yeah? So this here is a refrigerator. So this is one thermodynamic mode of the Canoe machine. This is a refrigerator. Yeah. So just, I should mention the following. So we talk here of efficiency. Of course, if you think about a refrigerator, then you probably would define efficiency in a different way. Yeah, you wouldn't say that the product that you want is the work, quite in the contrary. You would say the product or the desired quantity is the heat that you remove. So this is actually Q2, right? And you would ask, how much kilowatts of Q2 can I remove with 1 kilowatt of electricity? This is what you would use as a coefficient of performance for a refrigerator. But we use here the efficiency, the Canoe efficiency. Well, and if it's a refrigerator, then this Canoe efficiency must be smaller than 0. Yeah? So let's discuss the case where the efficiency is larger than 0. So first, the well-known one, namely the case where eta is larger than 0 at W is larger than 0. So there's a question. We can't see the handwriting. Thank you. So the case where the efficiency is larger than 0 and the work is larger than 0. And this means that also Q1 is larger than 0. And this is just the ordinary heat Wärmekraftmaschine, heat engine, supposed to do work. For this machine, this efficiency makes, is a good definition. And now we have the last one, the last case, namely that the efficiency is still larger than 0, sorry, but the work is smaller than 0. Yeah, so this means that that work goes in, right? But this is the direction of the heat flow. No. No, that can't be, of course. Yeah? So if the work is smaller than 0, then of course also this here must be smaller than 0 if we have eta larger than 0. So sorry. So the case where eta is larger than 0 at W is smaller than 0, which means that Q1 is also smaller than 0, right? And this is a heat pump. This is a heat pump. Yeah, so what you do is that you take kilowatt hours, joules, from the surrounding, and you move from the cold surrounding and you move it to your warm home in order to make it even warmer. Yeah, so that's the goal. And the question is, how many kilowatt hours can you take from your garden and get it into your home if you invest 1 kilowatt hour of precious energy in the form of electricity, say. Yeah? And this we would call the coefficient of performance for a heat pump, but this is not what we are interested here. We just stick with here the efficiency. Yeah? Yeah, so Q, this is a heat pump. Yeah. Note that T2 is smaller than T1. Yeah. And as a remark, eta is not the coefficient of performance, because the coefficient of performance should be larger than 1. Yeah, so for a good, well, it depends, of course, a little bit on the temperatures. Well, it depends quite a bit on the temperatures that you use. But the coefficient of performance should be, well, substantially higher than 1. Yeah, 3, 4, 5, or even higher. So it's not the coefficient of performance that you would see on a data sheet of a heat pump. But this is just a side remark. Yeah? So we are not interested in heat pumps or something like that. Yeah? And now we do the analogous discussion for the Curzon-Albon machine, which is a little bit more involved. It's a little bit more complex. So, yeah, same thing for the Curzon-Albon machine. So, we look at the first case that we take, right? We do it in a similar way, actually. Yeah. So here up, we had also eta smaller than 0, and so we do say the same thing here. Namely, we say eta is smaller than 0, which means that eta is between -infinity to 0. Yeah, so this is how we write it here. So 5. The first case would be eta between -infinity and 0, right? And if you look up here, then this was a refrigerator, right? And so now let's look how it is here. So here we use that eta is equal to 1 minus T4 over T3. Right? And from this, we find that T4 must be larger than T3. Right? And from this, we would conclude that, that T2 is larger than T1. So otherwise heat wouldn't flow. And if we now plug this into 15, so into this equation, so if we use this equation, then we find that the work is smaller than 0. So that we have to put in work. So we see that it's actually pretty much the same than before. So this is a refrigerator. So the next case that we look at is when the efficiency is between 0 and the Canoe efficiency. So efficiency is between 0 and the Canoe efficiency. And the Canoe efficiency is, of course, well, Canoe efficiency, here is the Curzon-Albon machine. Maybe I get this, this sketch once again. I put it here. So here's the Canoe Engine. For the Canoe efficiency, we had 1 minus T2 over T1. And well, this is just the generic case of a heat engine that is supposed to deliver work. This is the generic case of a heat engine supposed to deliver work. So the next case is that we look for the strange case where the efficiency is larger than the Canoe efficiency. So you might say this can't be the case, but wait a minute. So what we'll see is that this corresponds to a heat pump. So the Canoe efficiency is smaller than the efficiency, and this is smaller than 1. Looks strange at first glance. But we'll see that this is the heat pump. So, and in order to see this, we look at, limiting cases, which actually are also relevant here for these cases, for these two upper cases that we discussed already. We would first look at the case where the efficiency is equal to, or goes to minus infinity. So we look at a few limiting cases. And the first one would be that eta goes to minus infinity, right? Then if you remember this equation 10, where we had Q1 is equal to G times T1 minus G times T2 minus, divided by 1 over, T2 divided by 1 minus eta. Right? So now if we let go eta to minus infinity, then we see that this here goes to G times T1. Right? So and what we see is that this is kind of the maximum heat that can flow. This is the saturation heat. So then we have that Q1 is equal to G times T1, which we define as the saturation heat. It's a refrigerator, as we discussed already, right? So eta smaller 0, this means it's a refrigerator. And now if we say that eta is much smaller than 0, then this means, of course, that T4 is much larger than T3. Right? Which means that a lot of heat has to be transported to T1, right? And this is limited by the resistor R1. A lot of heat must be transported to T1, and this is limited by R1. And this gives the saturation. Okay, so the next one would be that the efficiency is actually equal to 0. What does it mean? When the efficiency is equal to 0, then this means, if you look at the efficiency here, then this means that these two temperatures are equal. And in other words, then this machine is kind of a shortcut. Well, if the efficiency is 0, then temperature difference is 0, then also the work is 0. This is a thermal short circuit. So eta equals 0. This means that T3 is equal to T4, and this means a thermal short circuit, I should say, I guess. Circuit. Well, the next thing that we could do is to discuss the case where eta is equal to the Canoe efficiency, right? So where eta is equal to the Canoe efficiency. What must be the case there? Well, you can derive this in different ways, but the most obvious way to see this is, well, if the entire machine here has to operate at the Canoe efficiency, then we know by definition that no entropy can be produced, which means that no heat can flow through this resistor, because if heat flows through this resistor, then there will be a temperature difference, and then there is entropy produced. And if entropy is produced, then the entire machine can't be a Canoe engine and can't have Canoe efficiency, right? So we know just from this simple argument, and you can actually derive it in different ways. You can see it in different ways. Well, actually, I write it down. Yeah? So what we then get is, so what we get is that Q1 is equal to 0, and this means that T1 minus T2 divided by 1 over eta, this was equation 10, is equal to 0, and then what we get is T1 is equal to T2 over 1 minus eta, And if we rearrange this, then we find that eta is equal to 1 minus T2 over T1, which is equal to the Canoe efficiency. And this is what we wanted to see. Yeah? Yeah? And Q1 equal to 0, this is obviously the opposite of the thermal short circuit. This is an open circuit. Yeah? Okay, then another limiting case here, namely that eta is equal to 1. Right? We use equation 11, and then we get that Q1 approaches G times T1 minus T1 minus T2. 1 minus 1, right? And you see that this goes to infinity. Yeah? So for eta equal to 1, an infinite heat would need to flow. Yeah? So, what does it mean? Yeah, so Q1 is negative. Yeah, the closer I go to eta equals to 1, the more negative Q1 gets. Yeah, so this means that heat is transported here upwards. Yeah? And we'll see, of course, that this is the heat pump. We said this already. Yeah? But what's the physical reason that the heat goes in the other direction, or how do we see this mathematically? Yeah? So what is the reason for Q1 smaller than 0? Right? So heat flows upwards. Well, what we have is that eta is equal to 1 minus T4 over T3, right? And in order to make eta larger than the Canoe efficiency, we need that the ratio of T1 over T2 is larger than the ratio of T4 over T3, right? In other words, T4 should get smaller and T3 larger, such that the ratio is smaller, yeah? And T3 larger. Now, for eta equals the Canoe efficiency, we had already that Q is equal to 0, right? Which means that T1 is equal to T3. So if T3 now has to get larger, then this means that the heat will flow in the upward direction. Yeah? So for eta equals to eta Canoe, we had T1 is equal to T3. We had T1 is equal to T3. Now we want to make T3 larger. Yeah, so T3 gets larger. This means T3 gets larger. This means that heat flows up. Yeah? now T3 must be larger. Then heat flows upwards. Yeah, and this is a heat pump. Okay, so these were the thermodynamic modes, and now we come to the characteristics, to the Kenlinian. But before we do this, I propose that we make a short break of 3 minutes or so, just to relax a little bit. So get a cup of tea or coffee, maybe a little bit late for coffee. And we would continue in a few minutes. So I'm not well prepared. I don't have a coffee with me, unfortunately. Perhaps you have some Christmas cake or so. I could actually decorate this a little bit here with some Christmas decoration. It looks ugly here in this room, doesn't it? So, and if you have questions, let me know. 3 minutes, I said. 3 minutes of break before we discuss the characteristics of that machine. And then we would derive an interesting law. Should be eta in the middle of the last aspect. What is aspect? So I think you mean here, right? Now it depends on what is the reference, right? So if this here is the reference, then you are right. But what I mean here is as a reference actually this machine up there. Yeah? Yeah. Yeah, perhaps I write for the Canoe Engine, for the Canoe case. Yeah? So everybody prepared for the characteristics of the machine? Then I would continue. Perhaps with the headline first. 3.3. Characteristics of the Curzon-Albon machine. I have a graph here. This one here. So this is the characteristics of the machine. No, stupid thing. Yeah. So now if you look at, so what I plotted there using Python, I guess, what I plotted there is just the following. Namely these equations, where do I have them? Oh, we wrote, yeah. So what I plotted here are just these two equations. Yeah? So this curve here is equation 11. That's equation 11. And that's equation 15. Yeah? And these curves contain everything that we discussed so far, these two curves. We found out that if the efficiency is equal to 0, this would be this point here, right? If the efficiency is equal to 0, actually it can be, not the efficiency. Yeah, well, if the efficiency is equal to 0, then the work that is produced is, of course, also equal to 0, right? The other interesting thing that we found was that if the efficiency is equal to the Canoe efficiency, then no entropy can be produced. So this is the blue curve is the entropy. No entropy can be produced, which means that no heat can flow. And if no heat can flow, then of course also due to the first law, also no work can be produced. So this is what you see here. Right? So the interesting thing here at this characteristics at this Ken linear for the work is that it goes at 2 points through 0, namely for eta equal to 0 and for eta equal to the Canoe efficiency. And in between, there should be a maximum, right? And we are going to calculate this maximum here. Why is this maximum interesting? Well, you always have to think of that this curve here is kind of, well, the number of dollars that you can earn. If you build a power plant, then you build it for the purpose to sell the work. Yeah, so you can convert the work in electricity, and you would sell electricity, right? So this is your income, so to say, and the heat are your expenses, or at least part of your expenses. At least these are the variable costs. So if you have a gas power plant, then the more heat you produce, the more gas you need, right? So this is the money that you need to spend, right? Well, and if you have a solar power plant, then of course the work is pretty much free. The heat is pretty much free, right? The sun shines, yeah, so if the sun shines all the time, but there you have fixed costs, namely the capital costs, the interest, right? This will define at which efficiency you will let run your machine. Yeah? Yes? So the optimum efficiency would be this. This is the highest possible efficiency, but nobody would run a machine at this efficiency because you don't earn money with it. Okay, let's write that down. So with characteristics, we mean characteristics. So I wanted to write the German word. Yeah, German Kennlinien. We mean the functional dependence of Q1W, the work, and the entropy on the efficiency. And the efficiency would be here defined as 1 minus T4 over T3, yeah, for the case of the Curzon-Albon machine. Yeah. So the relevance of these curves, at least the first two of them, of these curves, relates to economics. W is proportional to the number of dollars, let's be patriotic, euros, of course, is proportional to the number of euros produced, while Q1 is proportional to the expenses for fuel. Okay, and now the interesting point is, what is the maximum? What is the maximum? So where can I create the maximum income, so to say? Right? And this we want to derive. So the maximum of W as a function of eta is found by looking for the zero of the derivative. So I take the derivative with respect to the efficiency and look for its zero. And then if we use this equation 15, which defines the work, then we find that its derivative is T1 times eta squared minus 2 times T1 times eta plus T1 minus T2. And for this, we need to find the zero, right? And then you can look, then you can use the quadratic formula, quadratische Lösungsgleichung, Lösungsformel. So quadratic formula. Then you get that eta max eta max is not the maximum efficiency. Eta max is where the work is at its maximum. W max. This is nice formula, actually. Right? So looks almost like the Canoe efficiency, but there's a square root above this ratio of T2 and T1. And an immediate consequence is, of course, that the maximum, the point of maximum output of work has an efficiency that is smaller than the Canoe efficiency, of course, right? So, if, following discussion, so if the fuel is very cheap, right, then you would always run your heat engine at the maximum efficiency or close to the maximum efficiency. If the fuel is very expensive, then you would go closer to this. Yes, you would go closer to the Canoe engine, to the Canoe efficiency, right? And well, since the maximum is always flat and close to the maximum, by definition, usually the efficiency is at least a little bit to the right of the maximum. Very beautiful thing here, I think. Yeah, so the next thing that one could do is to look at the entropy, but that's perhaps not so interesting. What we can do is to look at to compare the efficiency of the Canoe and the Curzon-Alborn machine as a function of the ratio of the temperatures. Yeah? So, and for this I have another figure. Oh yeah, it's not available. I made a mistake here. It's probably a PDF here. Okay, anyway, then I have to draw it by hand. So this would look like this. So what we have here on the y-axis is eta, and on the x-axis we have the ratio of T2 over T1. Right? And if this here is 1, and here this would be 0. Right? So when this ratio is 1, then both are equal, of course. In the other case, T2 is equal to 0 or smaller as compared to T1. Right? This is a huge temperature difference. Therefore, we would expect a high efficiency there. And for the Canoe case, we would get something that looks like this. Should go to 0. Can I move this? Something like this, yeah? And this here would be 1. And here eta would be equal to 0. And for the Curzon-Alborn machine, we have a curve like this. Okay, let's look for an example. And what we do is that we look at the example of a nuclear power plant, namely Brockdorf in Schleswig-Holstein, so in the north of Germany. Let me see whether I have a graph here, a figure. No, unfortunately not. Okay. Anyway, example. Nuclear power plant, Brockdorf, in Schleswig-Holstein. It's one of the most powerful nuclear power plants, actually. So a single block delivers 1.4 gigawatt. It's one of the more modern nuclear power plants in Germany. Came in operation, well, more than 30 years ago, in 1985 or so, and will be switched off for good in a little bit more than a year at the latest. Yeah. So, and what we have there is the following. So the upper heat level there, yeah, so the temperature in the reactor is 280 degrees Celsius. So you see that that people are cautious or, well, are respectful a little bit. Yeah? So one doesn't run these nuclear power plants at high temperatures. Well, for a good reason. Yeah? So they use just 280 degrees or 553 Kelvin. The upper temperature level. Yeah, so in the inside of where the nuclear fuel sits is 280 degrees Celsius equal to 553 Kelvin. The lower level is the river. I don't know at which river. Probably it's, I didn't look it up. And for this we write 20 degrees Celsius, yeah, or 293 Kelvin. Okay, now in the literature you can also find a value that you could identify with T3. Well, I'm not sure whether this number makes sense that I have in the script. Sorry for that. So what we now would do is to first calculate the Canoe efficiency. Yeah, so pretend that this is a Canoe engine. Yeah, so the Canoe efficiency, this would be 1 minus T2 over T1, or 1 minus 293 Kelvin divided by 553 Kelvin. And what you would get is 0.47 as an efficiency. Now if we do the same thing for the maximum work generated by the power plant, then we would find, then we would calculate, well, I call it Curzon-Albon efficiency, also this is inaccurate. Then we would calculate this one here, right? And there you find 0.272. And there's a good reason to assume that they will operate it close to this maximum point here, because such a nuclear power plant is very expensive, while the fuel costs, well, I wouldn't say almost nothing, but the fuel is rather cheap. If you compare this to a gas power station, because you have much lower risks, yeah, so a gas power plant is much cheaper, but the fuel is rather expensive, right? And therefore, the gas power plant, you might decide to operate somewhere here, but the nuclear power plant, you would operate close to the maximum because all the costs occur due to interest, yeah, to financial costs. Well, of course, this power plant is out of the books since a long time, more or less. Yeah, so written off. But now let's compare it to the actual efficiency. Yeah, so the actual efficiency, one can look up on the internet. Yeah, you just look up how much of power it produces, namely these 1.4, almost 1.5 gigawatts. So here I have megawatts, 1,480 megawatts, and the thermal power of this machine is almost 4 gigawatts. Yeah. And what you get is then 0.38. Right? So you see, we are somewhere, as I said, yeah, so we are somewhere in between these 2 points. We are closer to this maximum point here. Okay, yeah. So it's not quite operated at the maximum, where it generates maximum work, but somewhere in between. Okay, so that's it pretty much for today. What we would do the next time would be to look again at the Curzon-Albon machine. We'll call it actually Stefan Boltzmann machine, where we assume a different mode of heat transfer. Yeah, so here for this Curzon-Albon machine, we said that we have a heat conductor. But the next thing would be that we say, well, the heat is not transferred through material, but it's transferred through radiation. Yeah, so that we have radiation here between these 2 levels and also between these levels. Yeah? And so we will do pretty much the same thing. So for this mode of heat transfer, and find also characteristics for that. And what's the idea there? Well, the idea there is that that this internal part is actually the atmosphere of Earth or a planet, right? So say that this is the day side, which is the warmer thing, and this is the night side. And what the heat engine is doing is to try to find an equilibrium as quick as possible, right? So actually, wind is produced in order to facilitate and to level the temperature differences. And and the idea is kind of that the atmosphere is probably tending to do this as quick as possible, and therefore one might make the assumption that the work produced by the atmosphere is maximized. Yeah? So once again, the idea will be that we analyze this machine once again, but just a different heat transfer mechanism, right? So you know it goes by the force power. That's probably not mathematically not very beautiful to deal with. And of course, I will ask Mathematica to do the hard work. But we'll also use a simplification, namely that T2 is equal to 0, because, well, if you think about the Earth, it receives heat from the sun and it radiates it to space, right? And the temperature, so the background of space is pretty close to 0. Yeah, so this will simplify things a little bit. And we'll calculate the characteristics for that, right? So it will be similar curves, just a little bit not so smooth. Again, yeah, so the basic idea, so the kind of, the clever thing is to say, we look for the point where the work is maximized, and then we can kind of find the efficiency of the heat engine, which is Yeah, so the efficiency of the of Earth's atmosphere, which we treat as a heat engine. Yeah, and in this sense, we slowly develop in the direction of wind. Yeah, but for this, I thank you for your attention, and we'll do this. We'll do this next week. Today is the 1st, yeah, so this will be the 8th of December. I'm looking forward to see you again, and maybe I have Zoom then available. I hope you enjoyed it nevertheless. Thank you. Thank you.